going back the other way, integration. Now, at an extension 1 level, we don't actually integrate inverse trig. At extension 2 level, we will see techniques that will allow us to do it. But at extension 1, beyond them. So the integration here is really just going back the other way. So the standard integrals that we get in the exam, we get this one, dx on the square root of a squared minus x squared, which must have come from the inverse sine of x on a. However, in this case, you have a choice. Because remember, one was plus, one was minus. You could, if you wanted to, use minus the inverse cos of x on a. Both are correct. Okay? Now, interesting, what does the standard integral say? Standard integral just has inverse sine of x on a. It doesn't put the other one down. But there's no reason why you couldn't use minus the inverse cos. And so the other standard integral is dx on a squared plus x squared. And that one goes to inverse tan. But remember the difference. There was an a on the top of that one. So therefore we get 1 on a inverse tan. Very easy to forget the 1 on a there. Or the other common mistake is putting the 1 on a in front of the inverse sine, and it's not there. So dx over the square root of 4 minus x squared. What this means is in an extension 1 exam, you're really only going to see integrations that turn into linear functions. You very rarely, if ever, see ones where there's other functions involved, unless you use the technique integration by substitution, which of course we'll look at later. So this one just goes straight to inverse sine of x on 2, plus of course a constant. Dx on 9 plus x squared, well that's in the form of the second standard integral, so that becomes 1/3 inverse tan x on 3, plus of course a constant. Let's do a definite one, and you'll see these sort of numbers cropping up a lot because it then allows us to play with exact values. Inverse sine of x on root 2, but we're going from 0 to 1. So sub 1 in, we get inverse sine of 1 on root 2. Oh, that's convenient. We know what that one is. Minus inverse sine of 0. Oh, we know that one too. So inverse sine of 1 on root 2 is pi on 4. 0 is, of course, 0. The answer is pi on 4. You might get it in this form, where they say differentiate this, hence integrate this. So it's sort of like a big hit. Differentiate inverse sine e to the x. So that would be derivative on the square root of 1 minus the function squared. Oh my gosh, will you look at that? That happens to be the integral. So therefore, when I integrate e to the x on the square root of 1 minus e to the 2x, I must get inverse sine e to the x. Isn't maths amazing? And we're going from minus log 2 to 0. That becomes the interesting bit. Well, e to the 0, of course, is 1, so that's fine. E to the minus log 2. Remember, e to the log will cancel, but I've got to deal with that negative sign before it cancels. So I bring it in, it becomes 2 to the power of negative 1, which is, of course, a half. And then the e log cancels, leaving me with inverse sine of a half. So pi on 2 minus pi on 6, which is pi on 3. Here's one with 4 minus 9x squared. The standard integral was a squared minus x squared. How shall I deal with that? I'll make it look like a squared minus x squared. I could factorise the square root of 9, or 3. So it becomes dx on 3 lots of the square root of 4 minus x squared. So a now is 2/3. So I have a third. We bring the constant out the front. A third inverse sine 3x on 2. Because it would be x on a. We just said a was 2/3. But notice this. Look, you could have sort of guessed that was going to be 3x on 2 because you've got 9x squared and 4. So the a, if you like, is still going to turn out to be 2. The top 3x, would you have picked up the third if we didn't do it that way? So just be careful. If you want to just look at it and go, oh, I think that's going to be inverse sine 3x on 2, there is more happening in this question. So it might be an idea to factorise out and make sure. 1e